Hello and welcome to section 10.2. So we're going to start talking about exponential functions. So exponentials are probably one of the most applicable math functions in real life. You will see that it has to do with sort of population growth or bacteria growth, like how viruses multiply. It also has to do with a lot of financial stuff, like you put money in a bank and it earns interest, and it's like an exponential process. But also like decay, like carbon dating, like figuring out how old things are, depreciation of a value of a car, or appreciation of value of a house. So that's increased also. So there's a lot of real immediate applications of exponential functions. Okay, I'm going to talk about some applications a bit later on. So the basic equation of an exponential function is this. We have f of x equals a to the x. A is a constant, positive, and not equal to 1, right? So it can be like between 0 and 1, or 1 or more. So the base is a constant and the exponent is the variable. So this is why this is a bit different than all the others, because we've worked with exponents, but the exponents were the numbers and the variable was the base. So here they switch. Right? So this is the basic equation of an exponential function. So we're going to see what the basic graphs look like. All right. So on the same coordinate system, we're going to graph 2 to the x and 3 to the x. Okay, so let me make a coordinate grid here. I'll try to make it a bit better. There we go. And here. Okay, so we have 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think that's probably enough. Alright, so let's make a table of values. X and y equals 2 to the x power. Okay, and we're going to pick a few points. We're going to pick 0, 2 to the 0, anything to the 0 is 1. X is 1, 2 to the 1 is 2. X is 2. 2 to the 2 is 4. X is 3. 2 to the 3 is 8. Okay, and I'm going to pick lots of points because we don't know what this looks yet. So if you have no idea what the function looks like, you better make a table of lots of points to get a good idea. Okay, negative 1, 2 to the negative 1, it's a negative exponent. This means 1/2. Negative 2, 2 to negative 2 is 1 over 2 squared, which is 1 over 4. Negative 3, 2 to the negative 3 is 1 over 2 cubed, which is 1 over 8. Okay, so these are like 0.5, 0.25, 0.125. Alright, so I'm going to graph these. Alright, so 0 is 1, 1 is 2, 2 is 4, 3 is 8. Alright, and on this side we have 1/2, 1/4, 1/3. Okay, so I want you to notice a few things. The values of y are doubling. So 1 times 2, if I multiply this by 2, 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. Right? So this is what the base means. The base means that in order, as you incrementing the x, in order to go from one value of y to the next, it's doubling. Okay? And it happens here too, right? If I multiply 0.125 by 2, I get 0.25. Multiply by 2, I get 0.5. Multiply by 2, I get 1. Okay, so the values are doubling because the base is 2. Okay, so whatever the base is sort of what you're multiplying by to get the next value. The other thing I want you to notice is that it doesn't matter how far I go, like x is negative, the y value is never going to go negative because you're going 1 over 8, 1 over 16, 1 over 32, 1 over... So this is never going to be negative, okay? So on this side, it levels off. It's going to get really small, really close to 0, but never cross the x-axis because it doesn't go negative. And on this side, it shoots up. The number gets bigger, bigger, bigger. Like 16, 32, 64, 128. They double. So they get big really fast. So this is like exponential growth, right? So because when the function levels off like this, it goes flat and it doesn't pass a certain value, you say that there's an asymptote, a horizontal asymptote right here. Horizontal asymptote. Okay, so an asymptote means that the kind of value approaches a certain number and it never gets there, but it doesn't cross, it doesn't go on the other side. So it's like a barrier. It's a floor in this case. Okay, so this is what 2 to the x looks like. All right, let's graph 3 to the x. So I'm going to make a new table. I'm going to say y equals 3 to the x. Start with 0. 3 to the 0 is 1 again. 3 to the 1 is 3. 3 to the 2, so this is 2. 3 to the 2 is 9. 3. 3 to the 3 is 27. Ooh, those numbers are getting much bigger because we're multiplying by 3 now. So 1 times 3 is 3, times 3 is 9, times 3 is 27. So they're getting faster, a lot quicker. At negative 1, we have 3 to the negative 1, which is 1/3. Negative 2, we have 3 to the negative 2, which is 1 over 9. And negative 3, 3 to the negative 3 is 1 over 27. So these numbers are like a lot smaller. So this is like 0.3, this is 0.1, this is like 0.0 something. Okay, again, it doesn't, let me actually find out what it is. 1 divided by 27, 0.04. Okay, so let's graph. So they meet at 1. When x is 0, this is always going to be 1. But then you have 1, 3, 2, 9, and 327 is like off the screen. I'm not even going to go there. And then it's below 1/3, 1/9, 1 over 27. So here it still levels off. It doesn't go negative. And it's sort of crossing at y is 1. And then it shoots up even quicker. Right? So it goes like this, 3 to the x. Right? So as we change the base, as we increase the base of the exponent, the exponential becomes steeper, but it looks the same, right? It's kind of the same behavior. All right? So here we just starting to look at what the basic exponential graphs look like.